Let's expand further on the elements of the Standard Model and begin by elaborating on bosons and fermions. Let's look back at some examples of bosons, like a photon, a Higgs boson, and a doubly boson. The photon and the doubly boson are examples of vector bosons, while the Higgs boson is an example of a scalar boson. This classification is based on something called the spin of these particles. Now, to be clear, these particles don't literally spin. It's best to just consider spin as an inherent property of the particle, like its charge. It's worth noting that the vector bosons are carriers of fundamental forces, and have a spin of 1, while the scalar boson has a spin of 0, and does not carry a fundamental force with it. Now let's look at some fermions. Some examples are the top, the anticharm, and the strange, all of which are quarks. We have so far defined bosons and fermions based on whether they are force-carrying particles or matter particles. This definition holds for fundamental particles. When considering all particles, fundamental and composite, a definition based on spin of the particles is used. All fermions have half-integer spin, so spin like a half, 3/2, 5/2, etc. While bosons have integer spin, or in simpler terms, whole numbers like 0, 1, 2, etc. Bosons and fermions obey different statistics. This means that when a group of identical particles are present, they behave differently depending on whether the particles are bosons or fermions. Bosons obey Bose-Einstein statistics, which is given by the following equation. Fermions obey Fermi-Dirac statistics, which is given by the following equation. A more qualitative difference between them is that bosons can all bunch into one quantum state, whilst fermions cannot. If you're familiar with electron orbitals in atoms, these orbitals are in fact a consequence of electrons being fermions.